On July 12th, 2022, a photograph was released to the public. It had taken 25 years to build the machine that took it. $10 billion. A mirror the size of a tennis court, folded like origami to fit inside a rocket, then unfolded, alone, 1,000,000 miles from Earth, with a precision that engineers described as equivalent to measuring the distance from New York to Los Angeles, down to the width of a human hair. The photograph showed a patch of sky the size of a grain of sand held at arm's length. In that grain of sand, thousands of galaxies, each one containing hundreds of billions of stars. Some of them, the ones glowing red and distorted at the edges of the image, were so far away that the light reaching the telescope had been traveling for more than 13 billion years. We were looking at light that left its source before the Earth existed, before the Sun existed, when the universe itself was less than 5% of its current age. That image had a name, the James Webb Deep Field, and it was the most beautiful thing humanity had ever seen. But beauty was not the problem. The problem was what the galaxies in that image were doing, and when they were doing it. Because what Webb found, in that image and in the thousands of observations that followed, did not match what we thought we knew. It did not confirm the model. It broke it. To understand why Webb's findings were so disorienting, you need to understand what we thought the early universe looked like. The standard model of cosmology, the framework that had guided astrophysics for decades, described the early universe as a place of elegant simplicity. After the Big Bang, matter was distributed almost perfectly evenly. Gravity began pulling that matter together into clouds. The clouds collapsed into the first stars, which were massive, unstable, and short-lived. Those first stars died, seeding the universe with heavier elements. Over hundreds of millions of years, those elements coalesced into the first galaxies, small, irregular, chaotic. Then, over billions more years, those small galaxies merged and grew into the large, structured galaxies we see today. It was a story of gradual becoming, of complexity earned slowly over deep time. The early universe, in this model, was a rough draft. What we have now, the Milky Way, Andromeda, the organized spirals and ellipticals, was the finished work, the product of billions of years of cosmic evolution. We were confident in this model, not tentatively confident, structurally confident. It had been tested against observation after observation, refined over decades, supported by the best data we had. The best data we had, it turned out, was not good enough, because Webb could see further than anything we had ever built. And what it saw when it looked at the early universe, at those first few 100 million years after the Big Bang, was not a rough draft. It was a finished painting we had no explanation for. The first anomaly appeared almost immediately. Webb began observing what astronomers call high redshift objects, galaxies so far away that the expansion of the universe has stretched their light from ultraviolet all the way into the infrared, shifting them far beyond what Hubble could detect. Webb was designed to see exactly this, and it did. What it was not designed to find, what nobody expected it to find, were galaxies at those distances that were already massive, already structured, already containing hundreds of billions of stars, organized into recognizable forms, glowing with the steady light of mature stellar populations. These galaxies were being observed as they existed roughly 500 to 700 million years after the Big Bang. In the standard model, that is infancy. That is the rough draft phase. There should not have been time, not nearly enough time, for gravity to assemble that much matter, ignite that many stars, process that many generations of stellar life and death, and produce what Webb was seeing. Astronomers called them, with a mixture of excitement and unease, massive early galaxies. One, observed in early 2023, was estimated to contain as many stars as the Milky Way, our galaxy, which took 13 billion years to build, and it existed when the universe was less than 700 million years old. The researchers who published the findings described them, in the measured language of scientific papers, as being in tension with standard models of galaxy formation. In the measured language of everyone else, they should not exist. The image Webb produced of these galaxies is the second thing that stops you, not the deep field, though that stops you too. This one is different. These are bright, compact, structured. They look like galaxies that belong in the present-day universe, but they are being seen from a time when, according to everything we thought we understood, the universe was barely getting started. You are looking at something that should not be there, and it is beautiful. Science has a procedure for anomalies. First, you check your instrument. Webb went through the most rigorous calibration process in telescope history. Every mirror segment aligned, every detector verified, every measurement cross-checked against known objects. The instrument was not the problem. Then you check your data reduction. The process of converting raw detector signals into usable measurements is complex, and errors can hide in it. Teams around the world independently analyzed the Webb data. The data was not the problem. Then you check your assumptions. And this is where it gets genuinely interesting, because when you check your assumptions hard enough, you find that there are more of them than you realized. And some of them are load-bearing in ways you didn't fully appreciate until one of them started to crack. The assumption under the most pressure is called the star formation rate. This is the rate at which gas and dust collapse into stars within a given galaxy. The standard model predicts that in the early universe, this rate was relatively modest, not because the ingredients weren't there, but because the processes that drive star formation take time to organize themselves. What Webb is seeing implies a star formation rate in the early universe that is dramatically higher than our models predicted. High enough that galaxies could build to enormous size in a fraction of the time we thought possible. Which means either the physics of early star formation was fundamentally different from what we modeled, or the Big Bang itself seeded the universe with structure that our current models don't account for. Or something else entirely is happening that we do not yet have the language to describe. None of these options are small revisions. Each one is a structural change to how we understand cosmic history. What Webb revealed is not an anomaly at the edge of our knowledge, it is an anomaly at the center of it. And here is the thing about that, the thing that takes a moment to absorb. This is not a failure of science. This is science working exactly as it is supposed to. The model made predictions. The observations contradicted the predictions. The model must now change. This is not a crisis. It is a correction. But corrections of this scale are rare, and they always mean the same thing. We get to understand something new. Set aside the data for a moment. Set aside the redshift measurements and the stellar mass estimates and the star formation rate calculations. Set all of it aside and just look at what Webb has produced. The pillars of creation. First photographed by Hubble in 1995, an image so famous it became a poster on the walls of a generation. Webb photographed them again. The same pillars, the same towers of gas and dust inside the Eagle Nebula, 7,000 light-years away, where new stars are being born inside columns of molecular cloud. Hubble showed you the shape, Webb showed you the interior. Infrared light passes through dust that visible light cannot penetrate. Webb saw through the pillars and revealed, embedded inside them, dozens of newly forming stars. Protostars, still wrapped in their birth material, glowing with the heat of collapse. Stars that Hubble didn't know were there. Things that are happening right now, 7,000 light-years away, that we literally could not see until 2 years ago. Then there's Stephan's Quintet. 5 galaxies in a slow-motion collision. Hubble imaged them. Webb imaged them at a scale and resolution that produced the largest image the telescope had ever released, covering an area of sky equivalent to 1/5 the diameter of a full moon. In that image, you can trace the shock waves of galactic collision as visible structure. You can see where one galaxy's gravitational pull is drawing threads of stars out of another like taffy. You can see, in the colors, the difference between regions of active star formation and regions of ancient stellar populations. You are looking at a collision between entire galaxies. At the scale of the image, each smear of light contains more stars than there are grains of sand on every beach on Earth. And it is, in the most literal sense of the word, gorgeous. This is what Webb does that no specification sheet captures. It does not just extend our reach, it changes the quality of what we see. It makes the universe more detailed, more textured, more specific. And specificity, it turns out, produces awe in a way that abstraction never quite manages. You can be told that a galaxy contains 200 billion stars. You can nod and file that number somewhere in your mind, next to other very large numbers. It doesn't touch you. Then you see the Webb image of that galaxy, and it touches you. Here's what the James Webb Space Telescope is really about. Not the hardware, not the findings, not even the images. It is about what happens when a civilization decides to look further than it has ever looked, knowing it might not like what it sees, knowing the view might not confirm what it believes, doing it anyway. The model that Webb is currently stressing took decades to build. Careers were devoted to it. It was beautiful in the way that good models are beautiful, internally consistent, broadly predictive, elegant in its structure. And it may turn out to be wrong. Not wrong in its details, wrong in something closer to its bones. That is uncomfortable. And it is also the best thing that happens in science, because a wrong model that makes testable predictions is infinitely more valuable than no model at all. It got us here. It got us to the point where we could build Webb, aim it at the right patch of sky, and discover that the universe is more complex than we thought. Wrong models are how you find the right ones, but there is something else here. Something that sits beneath the astrophysics and the model revision and the scientific process. The James Webb Space Telescope is one of the most complex objects our civilization has ever built, folded 17 times to fit inside a rocket. Deployed autonomously in deep space, cooled to within a fraction of absolute zero so its own heat wouldn't contaminate its measurements. Every single component had to work perfectly on the first try, 1,000,000 miles from the nearest repair crew in an environment our bodies cannot survive for 30 seconds. And it worked. All of it. There is something worth sitting with in that. Not as a celebration of engineering, though it is that. As a statement about what humans are capable of when we decide that understanding something matters enough to try. We built a machine to look at the beginning of time, and it showed us things we didn't expect to see. And now we have to think differently. That is not a crisis, that is a gift. The James Webb Deep Field image covers a patch of sky that, to your naked eye, would appear completely empty. No stars visible, no galaxies, just dark. Point Webb at that darkness for 12 hours and it fills with light. Thousands of galaxies, each one 100 billion suns, stretching back to within a few 100 million years of the beginning of everything. The universe did not wait for us to be ready to see it. It has been out there, all of it, from the very start. We just needed a big enough mirror. And here is what I want you to take from this. We built that mirror with our hands. With mathematics that took centuries to develop, with engineering that didn't exist 20 years ago. We folded it 17 times, put it on a rocket, sent it 1,000,000 miles away, unfolded it in the dark, and aimed it at nothing. And it showed us that the universe is larger, older in its complexity, richer in its structure, and more surprising in its early behavior than we had any right to expect. The model was wrong. The universe is more. It is always more. Every time we have built a better instrument and pointed it at the sky, every single time without exception, the universe has turned out to be larger and stranger and more intricate than the instrument before it revealed. There is no reason to think Webb is the last mirror. There is every reason to think the next one will show us something we cannot currently imagine. And somewhere, in a patch of sky that looks completely empty, it is already waiting.